It looks like we're going live. Maybe.
Yeah, I'm not
Hey,
seeing any.
there it goes. You should see it in a second. Here, let's do
Yeah,
another one. I love
it's
these
live.
things.
No, yeah, that's cool. We're on, Bill. We're definitely live.
Ben,
Okay.
I hate technology, man. Let's make this Ben and Bil talk quilting or something.
No.
Do you like fishing? Let's go fishing. I'm done with this.
What,
So how you doing, my
What does
friend?
my T-shirt say?
I fish for bluefish. It's so. Now it's amazing though. In Australia, you guys actually still read from right to left, right?
Actually, that would be in the Middle East somewhere, but yeah.
So you read from left to right. Yeah.
We do have the Coriolis effect, though, so our toilets do flush the other way.
And
Water
guess what?
drains
The
down the sink. And I wonder if, actually, I've always wondered, and I don't know what scientific experiment one would actually have to set up to test this, but I wonder if current would do the same thing. If we could potentially, let's just imagine, be imaginative for a moment. What if we were able to create an electron sink? Which way would the electrons go into the sink?
So I've been reading or watching a video series on subatomic particles, and an electron that spins the other way is a positron. I mean, I always read about them, but now I understand to what degree they are the opposite of an electron field. So, and if you see Feynman diagrams, they even show time moves right to left, and you can go back and forward between an electron and an anti-electron, positron.
Bill, you're already above my pay grade there.
Sean Carroll does a series on the Higgs boson.
Yes. I am going to have to follow up on that because I know barely anything about quantum mechanics and subatomics. Yeah, you want to talk that stuff, you get Matt Bergeron on the show.
There you go.
He's all about reading up on all that stuff. I have 3 kids. He has 1, so he has extra time to read.
And I'm still trying to get the chat to work this time through. So we're running without chat. I mean, something breaks every time, right? So, hey, tell us about you changed jobs.
I did, and I was very careful about my communications around this because I was at Altium for 16 years and really had a great time there. For the most part, like any company, if you're around long enough, you're going to deal with people and politics and like that's going to happen anywhere. So,
right.
But aside from that, just watching where we went with the technology from when I started in 2004 with Protel DXP, and oddly enough, I joined Altium because I was an FPGA developer and wanted to write VHDL code and develop IP cores and work on hardware acceleration and embedded systems. And all of that was integrated into the product at that time. And they had no one in support. Yeah, they had no one in support who understood any of that stuff, except they had one other applications engineer, Stefan, who was also a really awesome guy. And he taught me a lot in my first days at Altium. But yeah, I mean, it
so
was
now where are you?
So after all that time, I wanted to make sure I explained to Altium's customers why I was moving on, because they all know who I am. I did a lot of marketing and videos and helped a lot of people. And now I'm at Autodesk working on Fusion. I'm working on and with Fusion 360. Which is super exciting. You can see I've got it open here in the background. It is now.
And this is Fusion 360 for printed circuit board layout and schematics, right?
It's for everything. It's for complete product design. We don't have embedded or FPGA, of course. Altium doesn't anymore either, which is something I was personally actually very disappointed and sad about. it was a practical decision if you're
Well,
maintaining.
at the end of the day, aren't you really just trying to get your pin swaps, like
Well,
keep them
yeah,
contained?
yeah, and
That's the whole reason to have them to get integrated.
that's what 90% of the users were telling people like me is, look, we get it, but we don't, like, we have another guy who's a specialist in that field, and he doesn't want to use Altium
Right.
Designer for coding VHDL. He wants to use the Xilinx tools, or he wants to use
Xilinx. Yeah.
Yeah, even though those tools are all god awful, in my opinion. They get the job done. Don't get me wrong; they're very powerful.
Oh,
tools.
yeah. No, most pros
But-
reach then up for mentors and things like that to wrap on top of the Altium layer, or I mean the Altera layer.
Well, and let's face it, the gurus in that field are using Sublime Text or Emacs. You know, they're not. They're like software developers. They have their own favorite systems on Linux, and they're really nerded out on scripting everything and using makefiles and doing everything from a command line and using Vim for their text editor or Emacs, or if they're on Windows or Mac, they probably use Sublime Text, which is an excellent text editor. But they do everything. They have this workflow that's very personalized. It's like the old analogy that went around the internet in the 90s. If aircraft were operating systems,
Right.
Bear in mind this was the 90s, and I actually run Windows 10, and I think Windows 10 is awesome, and I actually really like it. I'm not a huge fan of Microsoft, the company, necessarily, but Windows 10 is a great operating system. It's very nice, easy to use, super smooth, doesn't crash, fast. Okay, having said all that, in the 90s, Windows had a bad rap. Blue screens of death, you know. So the saying went that if aircraft were operating systems, well, Windows, you'd have a very nice, comfortable experience. The staff would be courteous and friendly and be very well dressed, and the aircraft
went screaming into the mountain.
Aircraft would look brand new. You'd have a great experience taking off, and then very shortly after takeoff, it would crash. Unix, on the other hand, everyone would have to bring their own piece of the aircraft with tools to the airport and do the final assembly, and the thing would be an ugly duckling. But once it would get into the air, it would be super hard to take off. Really difficult.
Right. Well, the joke I know is the dashboard would have a single light on it that's a question mark, and you would have to write the tool to figure out why the question mark came on the dashboard to tell you what the airplane's doing.
Yeah, but once in the air, it would be totally reliable. That's right. That was the joke, right? So,
hey, I did a PC board since I saw you last. So I'm working on a radar, right? Continuous wave frequency modulated radar, and I built a filter to take the output of the super heterodyne, basically. Yep. So now I just got this working yesterday as a triangle generator that sweeps the voltage controlled oscillator. And I did that with a PIC 16F 18855, where I just took one port and I made R2R ladder on it. Now I just increment the port decrement, and I have but I have a pretty reasonable triangle wave out of it.
Yeah.
So
you're doing DDS.
I can do DDS, yeah. I'm going to release it with, let me say, I'll do the triangle wave and I'll leave it to other people to do the other waves.
Yeah, why not?
Yeah.
And even,
so I have to learn how to use GitHub.
But even with, even with coding in C++ in Arduino, the little 8-bit microcontrollers today have enough memory that you could do any kind of more or less arbitrary waveform, and store the points, like you calculate it in one routine, and then store the points in memory and just play it out from memory.
And I am using interrupts to play it, because obviously you'd get jitter and everything else if you were just trying to do it in C. So I have the timer interrupt routine. He's the guy that goes in and says, real quick, bap, bap, and tries to get it done.
So I got a question for you, Bill. How do you deal with fractional frequency adjustments?
Well, right now it's just tuned to one frequency. What needs to be added is there's a pot and an ADC, and I need to read the pot in real time, but leave it laying for the interrupt routine. So it has to be a void external, whatever that word, not dynamic, but volatile. It has to be a volatile. Yeah.
Yeah.
So again, I might leave that for somebody else. It's running at the frequency I want, but I put a pot on there so somebody could adjust the frequency if they wanted.
So
as long as they write the code, it's like Unix. You have to bring your own toolbox, you know?
But that's the fun, right? And that's why a lot of electronics engineers in particular, or electrical engineers, are running Linux and other. I don't, because I wanted to be more cut to the chase productive, and I have to run other software, and it all runs on Windows. So.
Right. Hey, real quick, can you look at the stream and see if we've got any chat comments? Because I'm seeing none, but maybe. So if you're watching this, do a chat, anybody. We think we can make them appear on the screen.
I closed the YouTube tab because I didn't want to be distracted by ourselves.
Right, right. Okay, let me try.
I'll go right back to it, and I can see the chats there.
Oh, somebody put, hey, all right, it's working. Thank you. Oh my God, technology works. Oh, slit my wrists.
Don't do that, please.
Samurai engineer, yeah.
Right, so, I mean, we can answer live. I can also type in there if anyone was wondering. I'm Schematica. That's my main YouTube channel. I have some others that I have really not done any work on at all. I'm nowhere near on top of that, and I really feel bad about that because I need to get back to making content that helps people again. And,
well, if they're calling you Schematica, they're calling you much nicer names than they call me. I'll give you that.
So
you want to talk PC boards?
I was going to ask you for that triangle generator. Where'd you get it made? Who did the fab for you?
I did that one at JLC PCB, and it arrived in less than a week.
That's great.
I hit it. I hit DHL just right, showed up, and done. You know?
And when you go to JLC PCB, use their sort of standard 2-layer or 4-layer stack up. So
right.
They have a pretty good web UI to set it up, and you select FR4 or whatever, right?
Yeah, they do. And I always do black. You know, I got hooked on probably around the time I started using Altium. I switched to black solder mask.
It does look good. Black solder mask looks great.
And you know what's different these days?
It's not very good for prototypes though, because it's hard to.
Yes.
Unless you're going to have the PCB open in your CAD right next to you while you're troubleshooting.
Which I do. Yeah.
You want to be able to see through it, at least in part, to follow things around. That's what I find.
Now, I always lay a ground plane on at least one layer, so none of my boards you can hold up to the light and see anything through them anymore. So.
I think most boards seem to be like that today. It's so cheap to get 4 layers that it's almost a no-brainer to get 4 layers.
But I still throw a shield ground on the top, and that's habit. And also... you know, there's people that say that's vital for the production of the PCB to not have a printed circuit board with everything etched away except for a couple copper. You won't get good quality on those couple copper. So, apparently there's a dog killing another dog right above me. So if you hear that, that's...
I couldn't hear any. It sounded like you were shuffling around on your chair or something.
So that's what's going on up there.
So I wanted to ask you, can JLC and other similar fabs. So I like to use them. I like to use PCBcart.com. I like to use PCBWay is a good one.
PCBWay. I used to use Gold Phoenix a lot for when I was doing whole panels. Phoenix
and I like
Gold,
to use OshPark when I need something more quickly.
Yeah.
But with all of these, I've noted something, and I think you wanted to discuss this today, right? That's about signal integrity.
Yeah.
Because you did those videos, seeing if, comparing the more expensive impedance controlled service against the.
Oh, I took a cheap PCB controlled or a cheap printed circuit board and showed that the impedance was more than 10% different depending on what direction you went. Yeah. Now, again, it's a non-impedance controlled board. I was cheating when I did it, but still the results surprised me.
Yeah. Yeah.
So,
So
hang on, I'm going to grab that board while you talk.
okay, so I thought in response to that, we can look about what's the probably number one factor that's actually causing those impedance anomalies and poorer signal integrity in cheap boards. So I don't know if I can share
Yeah, sure.
my.
Let's talk weave. Let's talk. And this whole conversation started about what's in a printed circuit board, and the answer is epoxy resin. It's like fiberglass, only it's a lot better, right?
Right. So I'm going to.
Do a screen share, and I should see it here.
Yeah. My mouse just decided to get the low battery jitters right at the wrong time.
We should call this the no tech zone.
Okay, so let's do a Google search. You can see I'm doing it there. You search for 106 glass weave, you'll get on images, right? You'll get this.
Yeah.
And Bill,
how come?
Can you bring up my screen is shared to you through Skype, so I don't know if you can bring that up.
Yeah. Hang on, we'll do it that way. There it goes.
Right?
Yep. Very
and
good.
You see all this. So we all know, right? Printed circuit boards are made up of laminations of composite material, and it's layers of fiberglass weave with epoxy resin, and there's a lot of other additives they add into the epoxy to do things like make it flame proof and give it a very uniform dielectric constant as much as possible. But the epoxy has a low dielectric constant, very low, usually around the 2 to 3 range for dielectric constant. And the glass has a very high dielectric constant, up around the 9 range.
Which means that the low dielectric constant, electrons can find their way through, and the high dielectric constant, the electrons are more insulated?
Yeah.
Because glass is an insulator, the best insulator.
A high dielectric constant means it has more capacity to store energy in the form of an electric field. But it also means it's slower to rearrange the electron orbits in response to a field being imposed on it. Now, if you go to a cheap PCB manufacturer, or really any PCB manufacturer, and just specify generic FR4, which stands for flame retardant generation 4, right?
Right. It doesn't even deal with dielectric. It's flame retarded is what the FR means.
That's right. I use in my Bantam Tools desktop PCB mill, which I use for prototyping, I use FR1, which is the original old school Bakelite style. It's not using the same epoxy resins. It's using an older type of epoxy that's phenolic based, right?
Right.
And it's not for reinforcement. It's not using glass fibers. And if you think about this, in Australia we call it booker rod, but here I guess,
and we call it rebar.
Yeah, right. So when you're pouring a concrete slab, it's going to all crack to pieces in no time. It needs reinforcement to make it strong, and you lay steel mesh into it. And we're doing the same thing here with printed circuit board FR4, and the default FR4 is this 106. It's called 106 glass fiber, and it's really like the bare minimum. It's fairly uniform, but it has gaps in between everything, like a lattice.
And the holes are rectangular instead of square.
Yeah, which is why you get, if you had a vertical trace,
right?
If you hold the board up, so you're looking down on the top, and a vertical trace is not going to have the same impedance as a horizontal trace. And two traces side by side in a differential pair, one may be mostly over fiber, and the other may be mostly over space. And so one's going to have a different impedance and propagation delay than the one right next to it. And what do you know? Your differential pair is not exactly a differential pair anymore.
Right. Now, what do you think about tilting the board? And Altium had that built into it, didn't it? It could offset the board like 11 degrees, which is
Well,
kind
you
of
could
a
do that.
cheap way to do it. I don't do it, but some people
that
do.
was proposed. There was a research paper about 10 years ago showing that you could fabricate your board at about 12 degrees off the panel.
Yeah.
You'd waste some of the panel and it would cost you money. But any CAD tool
Right.
can tilt the board. I mean, all you have to
Yeah.
you just design the board and then you tell the fabricator, hey, I want this tilted in the panel 12 degrees. And they'll charge you
Right.
lots of money because you're wasting panel space.
Yeah.
So,
yeah.
But since then, there's much better ways of actually solving this problem. There was another screenshot I pulled up from that search. Which one is it?
Oh, there you go. That was a great one.
This is a really little one, so let me zoom in. Sorry. It's showing the different fiber weaves. So you could go to a 1080 fiber, which is a bit more coverage than a 106. It's a little bit better. But you can see with a 5 mil wide trace laid over that, actually maybe there's a 3 mil wide traces, but either way, if you're doing a modern high-speed design, these weaves are not really any good. You can get combinations of them, and they do use
I was going to
different
say,
mixes.
right, you can lay them on top of each other, but statistically, you're still taking a chance that all the apertures don't just line up a second time.
Right. So this actually gives you very poor signal integrity. And what's the best solution now? And again, if you're not otherwise specifying it when you get your boards made, they're just going to pick it for you, and they'll pick whatever's cheapest. So 1080 is a little bit better, but you can still see in the X direction, the fibers are a bit spread out, but in the Y on this micrograph, they're still bunched up. And so it's
now,
not going to give you
is this from
good...
rolling it? Was that rolled post weave?
Yeah, I would guess so. I've not been in a factory that produces the fibers for PCBs,
Right.
but I would guess that is the case. So the fiber naturally will spread before it's combined into the epoxy and set. And then, so what they do now is you can. Why is it doing this?
I like the one where there's no holes in it.
This is showing. This is showing. I'm showing it now. The same sort of trace micrograph over what's called spread glass. So they can take a 1080 or a 1086, which already has not many gaps in it, and they actually kind of pummel it with what's essentially like a series of flat hammers that hammer it down and force it to spread. So spread glass, yeah.
I would have thought it was a roller, but it's an impact, huh?
It's some kind of... It may depend on the factory, and they have their that's their intellectual property how they do it.
I was going to say they don't let you film it probably.
Yeah. So, hey, thanks, Andreas. That's a very nice comment. I'm glad that people learn things when we do this, because why would we do it otherwise? So
right.
So get spread glass. This is another micrograph. This one's called 1652. And so you'll note that these are all identified by some kind of number. And those are actually from IPC standards. So the good news is this is standardized material, and any factory, you could ask for Isola FR408, and that's what they'll give you if they have it
that's
installed.
their standard, yeah.
And that will probably be using by default a 1080 glass or a 1086, which is better for signal integrity than a 106, but it's sort of middle of the road. If you want a spread glass, you're going to ask specifically for a 1652 or equivalent, and IPC actually has a standard way of doing that called a 4000 series slash sheet.
But isn't it harder? The other thing we have to do with our layers, though, is build it back up to a standard thickness of a printed circuit board.
Yes.
And so a 4-layer board, we have to lay lots of these layers up to get it. But an 8-layer board is twice as easy. Is that a fair statement, or am I oversimplifying?
That's a fair statement. So basically, if you're doing a 4-layer PCB, you're going to
You have a lot more room to stuff.
the very middle of it is going to be a fairly standard thickness core that's already fully set and has many layers of glass to get up to that thickness. And then there's copper on both sides of that pre-clad. It'll be etched. Then on top of that, they'll laminate prepregs, and those prepregs will be very thin because you want your ground planes near the surface layers of the board for higher capacitance.
I made a model of a core to show how it's built up, because then the prepregs, so you buy this, they buy this and have skids full of this stuff, material of a certain thickness.
Yep.
And then they'll sandwich coppers and prepregs together, and like if that's the overlay, the solder mask, the solder screen, and they build it up, but they start with a core based on how thick they're trying to make the printed circuit board.
Yeah, and the core is pre-made.
Right.
And they'll have a bunch of different ones in stock. So normally the way to route a board is you have your core layer with your ground planes, or maybe a power and a ground plane, but don't rely on that for capacitance between power and ground, because they're further apart. The purpose is not to have high ground plane capacitance. The purpose is to have ground planes as reference planes for the adjacent layers that are getting laminated over the top of that, so you get good uniform microstrip impedances and performance.
These are good for impedance. This is bad for impedance.
Yeah, the prepreg is thin.
Right,
and
very
so
thin.
It gets
pre-pregnated with resin is what the word comes from, right?
Yeah, and so it will only have maybe 1 or 2 sheets of glass in it.
Right.
Whereas the cores will have many sheets of glass, all sort of within. Maybe I can find a good.
Well, here's something I did.
Of that too.
So
actually,
you know what we say where the energy is in the dielectric, not in the copper. If you look, what I did is I made this be fluorescent, because I'm trying to show that prepreg layers are actually where the energy is. So I was trying to show that this is kind of not lit up and these are lit up because that's where the energy of the fields are. And again, Ben and I don't talk about electrons near as much as we talk about electron fields.
Right. So where did this go? I got to zoom this one in. These micrographs are unfortunately.
Oh, I love these kind of pictures. Yeah.
But this one, it's kind of hard to see because it's fuzzy. It's because they're taken under a lot of magnification under a microscope. But you can see a through-hole barrel via or pad with, this looks like a 4-layer PCB where most of the core material distance is in the inner layer. Actually, surprisingly,
look at the gaps in the height too.
Yeah, surprisingly, this one has a thicker prepregs on the outer layers, which
so Carl's asking what we're looking at. We're looking at a cutaway of a 4-layer board magnified. So this is a through hole or a via on a board magnified to the point where you can see the little barrel of the connector of the via. Whoops, we lost you. You went wide out. Yeah, go back to that. That was a cool picture.
I'm gonna go. I want to find one better, because what I'm hoping to show is that you can actually see. Oh, I love these Euro circuits ones. These Euro circuits people have some of the coolest microsections on their websites.
So real quick, a shout out to all the guys doing the chatting too while you're pulling that up. That's a new thing we're doing today, and we hope to keep doing it. It really adds something to it to see you guys there. So thanks for the shout out, guys.
So let's zoom in here. This one's better and it's in color.
Yeah.
So what we're looking at there is a 4-layer stack up, and you can actually see what we're seeing is what looks like little eyes on a potato. That's actually the vertical glass weaves. We're staring into them where they've been chopped off. Right. And
this is pressed together under.
Yeah, they're all crushed under immense pressure. and during the lamination, it goes into a
Right.
hydraulic press with a lot of heat and pressure. And that's also some of the secret sauce of PCB fabrication.
Yes.
They all have their own formulas of how long and how much weight or pressure
Right.
they put
Because
on.
you don't want the board will get thicker again a little bit after you remove the pressure, unless you were able to set the adhesive. But setting the adhesive is time, and time is money.
And not only that, it's getting it to the desired thickness within a 10% tolerance or a 5% tolerance.
That's right.
Whatever you, the designer, specify, you have to tell them this board must be this thickness. And so you tell them what your stack up is going to be with all the thicknesses, and they have to know exactly how much pressure and time to do. And they might waste a panel or two if it's something new that they haven't done before.
Right. And that's where the NRE money, the when you go the old route through local manufacturers, you'll spend thousands as they keep trying to get this right empirically. They're pretty good at what they do, but they still have to run it, throw some away till they get you tuned in. So,
yeah.
Hey, can you show us a stack up? You used the word stack up. Can you show us a stack up and what that means?
It's the design of browsing around here.
Yeah, because I saw you had a picture of it earlier. That's why
I wanted to show this one too.
That's cool.
This shows the glass. We're looking at the glass fiber under here. Then there's resin.
Again, this is an edge-on shot of a PC board, and that's a PCB. That's a copper conductor on the top.
Yeah, that's a microstrip trace, and you see underneath it's very rough. So the copper is actually treated to make it have a rough surface, so it adheres well to the epoxy. And then over that trace, it's obviously surface layer. You can see the green solder mask over it.
But you'd think that roughing up copper would be good all the time, but it's not, is it?
Well, it means at high frequencies.
That's right.
You're with skin effect.
Right.
You're increasing loss because you're forcing your signal to travel through the rough, more and more of the rough.
Through the longer distance. So here it is, we're at odds with ourselves, right? We got to get the copper to stick to the board, but if we make it glossy smooth, which is good for high frequencies, it might delaminate or come off the board. But that's a great shot of the solder mask there.
Yeah. So you asked, Bill, you were asking about layer stack ups. This is what we meant.
there's a picture
your design of, and this is somebody's illustration.
Somebody else's, right? Yeah. We could show this in Altium or almost any tool, Proteus, but we're just grabbing this off the internet.
Yeah, Fusion 360 and Eagle.
Oh, there you go.
They all have some means of entering your basic layer stack up. So that's where you're deciding as part of your design configuration or design rules, however you want to call it. You're deciding how many copper layers you're going to have,
right,
and what the thicknesses of the dielectrics ought to be between them. And ideally, you need to specify and understand what materials you want to use. If your design is just for a basic circuit that's not high speed, like you want to do a little microcontroller board, like the triangle wave generator you just showed me, you're not really going to be that concerned with impedance control or high speed performance or signal integrity. If you're
go ahead.
Yep. Yeah, go ahead. There's questions.
Well, I was going to say, somebody just asked if we knew about this back in the 128 days. And the answer was that they handed me the cheapest material they could and said, make it work. So while I was aware of some of these things, it didn't make any difference. So also, Carl, that's a great idea for 6502, what I can do next week. By the way, we're going to try and do this every week if technology cooperates with us.
Yep.
We're going to, I can show what a 6502 looks like under the microscope. So, and somebody's saying that they to zoom in, pick an image and zoom in, would be my advice at this point. Ooh, that's a cool one there. Yeah.
This one?
Yeah. I don't think they can really see the images in this scale.
My mouse battery is dying, so I'm going to switch to the trackpad. I really like this one.
Darn that entropy.
Let's look at this. Okay, that's from an NCAB group article. But this image, let's do that one.
Oh,
in
there's
the
a
tab.
micro via.
Yeah, this one is, zoom in.
There's two
Okay.
micro vias, really.
Yeah, so this one's way
buried
more
via.
complex.
Yeah.
And you can see the glass weave again in the middle, and you can see flexible copper core. So instead of using regular pre-preg for this design, because it's rigid flex, they use a very thin polyimide layer.
Right.
And that also has slightly higher dielectric constant than regular FR4. So what that means is you get more capacitance between the adjacent copper layers on that one. So that can be used in the main rigid section for your power supply decoupling, as well as having capacitors on the surface of the board. And then to build structures like this, they have to do many lamination steps. They have to do the initial etching of these layers with the flexible circuit. They etch those separately. Then they laminate those together with buildup of FR4 prepregs on the inner layer and cores on the outside. They laminate those. Then they etch the copper off the outside and do through-hole drilling and plating. Then they laminate again to get more prepreg on the surface layers. And they laser or mechanically controlled depth drill micro vias with tiny drills.
They laser drill. Yes.
Yeah, and
cool.
The copper is underneath ready to receive the laser. So they can use like an ultraviolet. Ultraviolet lasers will eat away copper, but infrared lasers, the copper will reflect. So before they laminate the copper on the outer layer, they drill all the holes where they need to be with an infrared laser, and it stops where the copper landing pad is. And then they can laminate and plate in an etching plating bath, and it fills in the microvias with copper. So you can actually have BGA pads soldered directly.
Right.
Yeah, it's.
So tell me about drilling. Now, in the old days, we only had a certain number of drill sizes, and we could specify them, but what was it, like about 16 or 12 drill sizes to a drill head, and if you went above that, you had to have 2 drill steps. Nowadays, how much is done with laser drilling? Can they hit any size hole, or is there you still don't want more than 8 different hole sizes in your design?
You can have more than 8. It's really
unlimited almost, is the way I treat it. They'll round up and down to their common sizes in the overseas houses.
They will, and they will actually. Engineers at PCB fabricators and a lot of PCB designers, especially people that haven't been doing it for long, don't realize this. What you actually get, even if it works, is not what you sent them.
Right.
They will change
it's what
your
you
design.
sent. Yeah.
Even
it's
if
what they made
Gerbers,
out of what you sent.
Even if you send them Gerber files, what they're going to do is analyze your set of Gerbers and your requirements. And they're going to say, well, if we're going to meet that requirement, we're actually going to have to change some of these drill holes, some of these via holes over here. We're going to have to plate a bit extra. We're going to have to modify some of these copper shapes here, need to shrink down just a little bit.
And they do it for free these days. In the old days, this was part of working with the fab house, going round and round. And nowadays, they do it after you do an online submission.
They won't tell you. Yeah, they won't even tell you. They'll just do it.
Unless you screwed up real bad, then they'll tell you.
Yeah.
Then I had something still sitting off the board one day, and they told me about that. They're like, did you really mean to have a... Yeah, I'm like, no, sorry. I think it was a fiducial or something.
Yeah, so...
Cool.
Fun stuff.
Cool. Well, I learned something here. It's... So yeah, let's do this to answer Carl. We're going to be doing it next week. Whoops, we lost all the concurrent viewers. I wonder what happened there. So we were up to about 18 and it just dropped to 0. So I don't know if that means we're still streaming or not. But maybe that's also a good point to start to wind down.
Yeah. Well, it's to me. I'm looking. It says 26 watching now.
Oh really? And now it says 26.
Yeah.
So once more, software. Everybody raise your hand if you're a programmer. Now slap yourself with it.
Actually, that's what I've got on my desk here.
Well, it said the guy that just wrote a little triangle generator, right?
I've been messing around with these STM8 modules, that you can buy for $1. I love these things.
Slap. Somebody just slapped themselves.
I can't.
Yeah, those are cool.
And they finally have got easy to do, because you can get a free tooltip from Cosmic. Micro talks about the Cosmic C compilers. But somebody built an STDuino add-on that gives, it's based on the Small Devices C compiler, and it gives support to the Arduino IDE for programming and debugging these things. So I've been playing around with that, and I just can't believe how cheap these devices are. They have and other cool stuff.
So here's one of my little ditties. I've showed this once before, but let's see if we can get it to focus. But I'm actually doing old 50 centers and then soldering them in a little oven here. Now, actually, I want to do a hackaday about it, but it's just trying to find the time. But how to make your own circuit boards at home if you're into this. And I say that because you almost always need to invest in a hot air soldering iron or something.
It's worth it, actually. It's
I think so.
I had the privilege of traveling
to China. Yes, basic counts.
I had a privilege of traveling to China off and on again several years ago, and one of the trips I actually went to the Beijing Road in Shanghai as a big electronics market, and I went in there and bought a whole bunch of stuff, and among it was I got a desktop reflow oven.
Okay.
I got a solder paste hand dispensing sort of jig, and a few other bits and pieces for doing surface mount work at home. And I'll tell you, there's no going back. And even if you want to try the hot plate method, where you're only mounting boards, if you're only mounting components on the top side, you can actually even do it in an electric griddle hot plate. Right.
Here's my oven these days. It's using a Control Leo. Whoops.
Yeah, those are also, I looked into that, and I wanted to build one of those back in its first generation.
Yeah.
And but then I saw how cheap the 928A reflow ovens were in China, and I just went, I'll just get.
No, it's infrared. Yeah, it has nasty shadowing. It'll burn your parts and still not do all the things.
You got the smaller one. I got the bigger one. It doesn't do that.
Yeah. Well, actually, my son made this. He took a Black & Decker.
Yep. Those are excellent, by the way.
Yeah, and it's got a turbo heater, so you actually add heating elements, you add insulation, you add the Control Leo section to it, and it bakes up a nice part. This uses PIV. It uses it uses inverse kinematics, is the way I look at it, but it's
a PID control algorithm.
PID, right, not PIV. And it has a very extensive learning time. It takes over an hour to learn how to heat, but then it knows how to heat quickly and easily to the processor.
I love that.
All the math is up front.
Yeah.
So, yeah, I love these. My son's been making these. We've been giving them away and selling them to friends. So I was thinking about dumping them on eBay, maybe.
You should. Yeah, some of us don't have time to go through the project and put it all together. It might
and Band-Aids. Yeah, you need those gloves that keep you from getting those nasty metal cuts.
Yeah.
So, Control Leo. Somebody asked Control Leo. Google Control Leo 3, and you just spelled it correctly, Electron Ash. And they pre-make the ovens for you also, but they're like $800 or $900. So we buy the kits, and the Black & Decker oven costs $25 from Amazon.
The oven's actually arrives the cheapest part.
Yeah.
What's the Control Leo kit cost?
I want to say $100.
Yes, it's still dirt cheap. It's worth doing. Like, think of your time. Your time is precious. Don't hand solder surface mount parts. It's not worth it. And even don't solder through hole parts anymore if you can avoid it. Design your board surface mount and use an oven. Seriously. It saves you so much time. Don't waste your time doing things the old way.
So I don't even like to tin leads. Here's how I tin leads. I have a solder pot. We used to have big ones of these in production. But if you need to solder, you actually just dip it in solder. You know, you don't sit there and tin leads one at a time. You'll just go nuts in a production environment. Yeah, actually, I have one more thing. Electronic wire strippers. You ever seen these?
Oh, I've used those. I used to use those
they
on
heat up.
enameled.
Right. You
used
put
to
the
use
wire
those.
in there, clamp down, and pull, and the heat will do it. You can do like 4 at once, just strip them away, and then dip them in your little solder pot.
The one I used to use was mechanical, and it had a motor in it that rotated a three-way series of blades, and
yes,
it would strip off the enamel coating on magnet wire. And I used to use that when hand winding inductors for power supplies. When I was in my teens, I was at college. I worked at a power supply company, and I was assembling power supplies.
Okay. I started as a production technician doing digital scales, and they happen to be 6502 based, and this is like the late 70s. And that's one thing led to another, and I ended up at Commodore by sheer accident.
Well, we're all very grateful, Bill. All of us, aren't we?
Well, let's have some fun, though. This is fun. Now, this is the whole point why we're doing this, right? Is to just have some fun and not dink with the dang technology fighting us. So it was good to get a chance to talk to you finally.
Yeah.
It's been weeks since we've been able to do this.
You too. So next week I'll send out some invitations too. We'll see if we can get
Yeah. Now that we know we have a recipe, doesn't mean we won't have the cake fall next week, but at least we have the recipe this time. So wait, are you guys who I've seen doing this on Twitter? No, but we probably should. So our goal is to keep doing this at a regular time on YouTube so that you guys know where we're at, and then expand to Facebook. That's at least a start. Now, if the Facebook technology doesn't work, then we won't use it. If we can stream with Twitter, I'll ask a younger person than me how to do that.
Cool.
So, well, great seeing you again. And
you too, mate.
So same time next week?
Yeah, let's do it. Same time next week.
Oh, hey, let's do some exit things here. Wait a minute. Oh, I like that one.
We need to come up with a sound effect.
Yeah, we do. Well, I like the sound effects of this one. So tell us which one you like the best. Oh, see, this one doesn't self-start for some reason.
Cool.
There it goes.
And thanks everyone for joining too. And we didn't even announce it. That's really awesome. We appreciate you all. And
all right.
Yeah, let's see if we can build the snowball.
Yes. More importantly, have a safe weekend. Be safe in your lives, and we'll see you this time next week.
Yep. Cool.